Hello and welcome to another session of rewriting GOAP action planning algorithm from JavaScript to Rust. So in previous session I had an issue. I couldn't really understand how to add stuff to external array. Let me show you again. So in this JavaScript implementation, before calling sorry, the build graph method, we have leaves defined to store all the solutions we found uh, for the goal planning. And yeah, I know I could pass like a create a leaves array and have it explicitly mutable and pass leaves and stuff, and then I would just pass externally defined leaves here, would have it mutable here, and etc etc etc. But to be honest, this is better. I just received a list of leaves. Okay, so that's one. um, I expect to get a thing from the function, so the function gives it to me. So I'm not sure what I was thinking about in a JavaScript test implementation. I just hacked something. So this is the only thing that's different in JavaScript and Rust implementation actually. Because here I kind of have to, in Rust, have some more common sense in a way. Also, when I was adding stuff to leaves, Rust asked me to add lifetime annotations to make sure that the thing we're adding um, here uh, is coming from the same lifetime, uh, in the sense that we are adding stuff to leaves eventually, and this incoming G node we have is coming from a lifetime, and this will end up in a lifetime apparently. So that's one new cool thing I kind of figured out about this implementation. I also wrote this matching goal just to check if, like in here, if after we applied some post conditions from actions to the next state that we are at, and if this new updated state already conforms to some goals, uh, like actual goal state. For example, a character is killed, so the goal is achieved. So we are checking exactly that. So here I'm actually checking for existence of a goal. I don't care about the actual goal that was achieved. All I care is that it was achieved. So it's underscore. The Rust checker will not ask us to use it. And since we achieved the goal, we push it, just like in here. So I wasn't able to find a method to just find something, but at least so just to return boolean. But this could work too. I'm going through available goals, convert to iterator, find whatever I need. I compare the incoming state we have with the state that we expect in goal, and here we go, we found a leaf. And the cool thing is that it compiles and it actually prints out that it has one leaf. So this is the thing that I came up with, for now, in offline session of mine, it took me like maybe an hour, maybe more, yesterday, and it wasn't nice material to even show. Just struggling and figuring out why is it not working. But anyway, with that portion of code out of the way, I'm now going to implement this. So else I need to copy available actions. So this portion is for cases when we are at some state in goals already. If we're not, if we haven't reached the goal, then we are most probably going to go deeper, right, and find for other solutions with remaining actions that we haven't done yet. So let's next. Oh, come on. Slow down. Next. Available actions equals to. So how is it called up there? Oh yeah, available actions, just like that. Uh, Available actions. I really hope the borrow checker will not scream at us. So clone. So this is that. Now we need to make sure that from that array we remove the action that we are currently at as a key. And I haven't deleted anything from hash maps in Rust yet. So this is going to be something new for me. Maybe delete. Nope. Remove. Some key. So is this going to be key? All right. Okay, let's actually double check documentation. Oh, hash map. So we called remove. Yeah, let's make this bigger for a moment. So remove the key from a map, returning the value at the key if the key was previously in the map. The key may be borrowed. Remove entry, remove key from the map, returning the stored key and value. So it returns the entire thing with the key and the value, and this just gives us the value. Well, that's cool. I wonder why they decided to return something, but yeah, let's just remove. So we remove the key, and just to make sure, actually, since this is new for me, print line, then I'm gonna say was and next available actions dot, is there a size or length? Lengths? There's lengths. Okay, cool. So that's a method. And let's copy that to just know how much it actually, like to check what's the size of it after we delete it. Delete back. I is now. Alright, so let's hope it compiles. Crap. Um, oh, it should be mutable. Such a simple and stupid error, actually. Let mute something. Bam. Bam. Shit. It's a reference, so the data it refers cannot be borrowed as mutable. Consider changing this to be a mutable reference. Is it saying the same thing here? Ah. So again, this is not a tutorial. This is just a bunch of pain. So this is working here like that. If it's saying I should make it a reference, then why the hell not? Ah. I wish this was a live chat of some sort. I would be able to ask questions maybe. So yeah, consider changing to mutable. Oh yeah, I'm deleting. Shit. I saw Primogen was trying to do stuff and he was cloning stuff everywhere. And his code was kind of slower, but it was at least working. In my case, it's not even working. Alright, a sad fact, my AG action wasn't deriving clone trait, and for some reason the clone thing is behaving kind of weird, so instead I used just creating a new hash map of a type that I really want, like this, and then I cloned from available actions, and the thing that I wanted, like deleting a action from a newly created list, is smaller, which is fine. So let's remove that. So 3 lines of extra code, not too bad. And then what happens is I build another graph based on the available actions and the node I'm currently at. So maybe I'm going to just copy the stuff that already works. I really need to learn how to go to the last symbol, yank, and B. So I also need to call it something else because leaves are already defined. So this is leaves from internal, like, yeah, internal leaves. Leaves internal, I'm going to pass a next node, not a start node. Oh yeah, here it is, next node. Alright, reference to that. Next node. Then yeah, we pass the existing available goals. Available goals, I've got it used, yeah, in here. Whoops. Alright. I'm not using Vim to the fullest, so yeah, bear with me. Available goals. I'm passing goals around. Now, available goals is still a reference because I'm passing it as a reference, and the next available actions. So, next available actions. Next available actions. Oh no, let's check if it compiles first, because it will not. Oh, it compiled. Okay, why? Print ln. So this is internal leaves, and leaves internal lengths. Let's see how much it got. Wow. So apparently it catches quite a bunch. So since I'm bubbling up the leaves I get in this implementation, I need to add this thing I got here. I need to add that to what I have in here. And I think the method was append, yeah. I looked it up when I was kind of preparing. Append from leaves internal. Okay, apparently it wants to have it as a mutable thing. Reference. Maybe like this. Oh no. What is it saying? Yep, need to figure out this now. This is so hard. Alright, so research time. Alright, so I found some solution. Um, I basically made a bunch of changes. I started working with indexes. Instead of having a list of, not a list, instead of having a tree, let's look at the G node. Instead of having a, a reference to actual node, a reference, I'm storing a variable like an option index. An index. All right. And the thing that's happening right now is in execute function. I mean, the implementation is purely prototypical right now, but I've got a list of nodes that we are creating generally. We came in with a graph function, build graph. We create some sort of next node, right? And I'm just adding that to a mutable list of nodes, just like that. And it's storing um, like option sum start index. Um, in regards to starting a node that we start from, in this case it's just none. Okay, so this is a clue for us that there's no node like farther in the root. So this is nice. And in leaves, I don't store nodes again in leaves because it's like a borrow checker um, nightmare. So I store indexes to nodes that we create in the nodes list. So this way, technically, when we create a node, we store it in an array, which is in the lifetime of execute function. So we take ownership of the nodes that we create. And in matching a goal function, I'm double checking if I'm currently at the cheapest cost possible. Right now, I do it in a functional, really stupid way just to see, like explore how I can improve on the functionality and the speed maybe. So I'm storing the um, cheapest action list possible to achieve a goal. And going deeper in the recursion, let's go down. Going deeper in the recursion, I'm passing this cheapest thing. And as we go deeper and deeper, we remember, okay, something was at the price of 8. It's way cheaper than initial 10,000 or whatever I said. So I start off with, yeah, is it 10,000? Yeah, 10,000. This is my price, like I'm setting up the initial price is way too high, and as our running costs assemble and we achieve a goal, we know that something is like way cheaper than this. I don't expect in this stupid implementation anything to be larger than this. If if at some point I do encounter the price of implementation bigger than this, I'll just go straight for max value of U size. What is that? I32 without negative signs. So yeah. So what actually is happening at this point? So I'm going deeper in graphs and fetching more and more cheaper implementations, but I still push that to a leaves count. Technically, I don't think I really need to do that. I don't need to do that because essentially I would only need to have the reference to a cheapest, not a reference, an index of a cheapest node. And the node itself, which had the cheapest implementation cost to achieve a goal, is already having a reference as an index to a node where it came from. Okay. So what I'm doing here is right after I get all the leaves, which you know succeeded in finding a cheaper solution, I iterate the indexes of leaves, indexes of nodes that turned out to be leaves, and I just check if the index, if the node at index is the root of it at least is something. It's not a none, and I just print it out until we reach the none, like the actual root object. Isn't that nice? This is actually quite impressive. I achieved a graph structure with bare minimum, actually, without any references, with just indexes, as if I was in C. I find this approach quite powerful, and yeah, indeed, when I run it, I've got several implementations which are not exactly full. What I mean is, here you can see, like in comparison to what I had in JavaScript, we do get a search weapon. We can pick it up, search ammo, pick up ammo, scout with weapon. Okay, in one of the implementations, it scouts suicidal, which is possibly cheaper. Then there is a oh yeah, and it's able to aim. So this is actually a duplicate, right? Aiming, and for some reason it's not adding attack with weapon. So I might have messed up somewhere in my state setup, like initial state setup, and it kind of shoots already. Maybe, I don't know. but technically it did find some solution, and the cheapest it found is I guess 7. So I'll need to double check why is it not showing me the first item, but it's really cool. So yeah, this is my implementation of GOAP algorithm. It's not finished yet, but at least it's giving me some information about what the character can do based on IDs of actions. So in the next session, I will probably clean that up. I will clean that up more off screen, not recording. And then I will show you how it actually looks. Maybe I will make this entire thing into a like struct so that I don't need to pass a lot of variables through the function. It feels kind of weird, but yeah, um, it does take quite a long time to process, 5 milliseconds, but to be fair, the output of this information here is done after the implementation was found. Here the timer is actually set to uh, the timer is set right after we print it out. So printing out stuff is actually taking some time. So maybe if I remove that temporarily, it's debug information. If I remove the other debug information, all right, it will not show us the solution. Okay, it's slower. Let's run it in release. So it's probably, yeah, at the same speed as it's at the same speed as JavaScript implementation, but it's probably because I'm not doing something right on the Rust side. So technically, when I convert this stuff and I stop passing around things in functions and maybe I copy hash maps a bit less, it will be faster. Till next time.